In discussing the wave function collapse, I remember that the simulation that you've seen before, it has detectors in it. And I would like to demonstrate the wave function collapse in the simulation. So remember that I can send a particle, let's say a neutron. So here's the wave function of the neutron. It's probably plotting the square of the amplitude of the wave function. So here's the real part. Here's the imaginary part. Here's the phase, right? Color represents the phase. So here's the magnitude. This glob, it's a wave packet. And when it hits the screen performs a detection, ping, right there. Another one, and ping, right there. Okay, but I can place a detector somewhere else. So I'm gonna add a detector. Okay, so there are several ways of detecting. I can do auto detect, or I can do manual detect. So when I press detect, I think it tries to detect the particle. Now, if I place the detector somewhere off to the side and I detect, it will not detect anything. So the probability of detection is related to how much the wave function overlaps with the detector. So now I'm going to place detector right on the pathway. I'm going to press detect. And you can see then when I press detect, it collapsed the wave function to where the detector is. Let me do this again. And hop. I can place the detector a little bit off center. The wave function overlaps, and boom, right here, wave function overlaps. So there's a large probability of detection at the position of the detector. And when I do make the detection, I collapse the wave function at the point where I detect the particle, which is where the detector is, right? And right. So let me try this again, and hop, I detected the particle. And detection drastically modifies the wave function. I detect, and after that, I release the particle, and its wave function continues to evolve, governed by the Schrodinger's equation. It evolves in some complicated way, but it's certainly different than if I didn't detect, right? The wave function is certainly different. Now, what if I keep detecting the particle? So there's a feature called repeat detect. If I just run it like this on its own, it's not really going to work. I can set an auto detect, and it's going to try to keep detecting the particle. And you can see when I keep detecting the particle, it's running an auto detect with a repeat feature. So it keeps auto detect means I don't have to press the detect. It tries to automatically detect the particle. And it does it in a repeated fashion. And you can see that it keeps trying to recollapse. It keeps recollapsing the wave function. Let me do this semi-main. So I can keep doing this. 1 second, let me show you. I have to do it at the right spot. I can keep doing this. If I keep detecting, I keep recollapsing the wave function, and I don't let the wave function move because I keep recollapsing it. And so if I continuously observe a particle, I prevent its wave function from evolving. This is an interesting quantum effect. It has a name. It's called quantum Zeno effect. And let me try to demonstrate again. So if I keep detecting it continuously, I prevent the wave function from evolving because I keep recollapsing it. If I stop, then it will evolve. So that's the collapse of the wave function upon detection. Let's go back to double slits. Remember when I discussed the double slits, well, I said, well, if you cover one of the slits, the outcome is very drastically different. And that's really what led us to the wave description of particle, because with paths, it doesn't matter. You just, instead of two globs, you're just gonna get one glob. But that's not what happens. First of all, it's never two globs, it's a periodic pattern. And when you cover one of the slits, you get a different type of periodic pattern. It's not like half of the first pattern. And we understand that's because when you put an obstacle, the way the wave diffracts through an obstacle is different. But even more interestingly, if you try to sneak a peek without really blocking the slit, if you try to catch if you try to glimpse where the particle passed, you destroy the whole pattern. Now, in order to learn, in order to obtain information where the particle passed, the detector must interact with the wave function. Our original idea was that, well, if the particle behaves classically, I can sneak a peek of where it passes. Now, what you're actually doing where you're trying to sneak a peek is you're placing the detector, and that detector interacts with the wave function. And that collapses the wave function and drastically modifies the wave function. So now let me place the detector here. Let me see, I'm gonna add a detector. Move the detector to the side first, and this is the diffraction of the wave packet, right? So you see a diffraction pattern. And now I'm gonna place a detector here. And just as the wave packet, so I can do an auto detect, for example, right? So I can do an auto detect, and when the wave packet passes, boom, the presence of the detector there collapses the wave function. So the subsequent evolution of the wave function is very different. Once you collapse the wave function, there's hardly any wave on this slit, so it's effectively almost like a single slit diffraction. Let me remove the auto detector. I'll just try to detect manually. Oh, you see, by detecting manually, I collapse the wave function. And once I release the particle, the wave function evolves very differently. Basically, it's almost like essentially the other slit doesn't matter. So by detecting, I change, by detecting the particle, but trying to catch, if I try to apply my classical thinking, I'm going to catch where the particle passed. What I'm actually doing is by placing the detector, as long as the detector interacts with the wave function, and that's what's needed in order to learn anything about the particle. And as long as it interacts with the wave function, it will, there's a probability that it will collapse the wave function. Now, what if the detector is somewhere out here? If it doesn't interact with the wave function very much, well, then the probability to collapse the wave function is very small. You see, I can try to detect, but it doesn't really detect. It doesn't interact with the wave function. But if I place the detector here, still not much. But if I place the detector here, there's a stronger overlap, and it collapses the wave function. Some weak overlap. But if I do it here like this, that collapses the wave function and then modifies the wave function. So that really explains why sneaking a peek of where the particle passed, that's the classical intuition, doesn't work. Now, if your detector doesn't interact with the wave function, then it's equivalent to not being able to detect the particle, and then it wouldn't, of course, collapse the wave function. So by placing a detector that does interact with the wave function, you will modify the wave function drastically. And that's why the outcome on the screen after that would be very different, because the wave function is modified. So that's the wave function collapse for you. All right, thanks.